Hello, lovely soul. Some nights the moon hangs so close you could reach up and brush your fingers against its light. You've seen that face 1,000 times, the same shadows, the same patterns, the same quiet glow. Maybe you've never thought to ask why. Maybe it's just always been there watching back. But here's the thing that keeps astronomers awake at night. The moon has another face, a whole other side. And you've never seen it. Not once, not in your entire life. Neither did your grandmother, neither did anyone who came before her stretching back through all of human history. The moon shows us only one side, always, forever. Why? Before we drift into that question, if you find comfort in these quiet journeys through the cosmos, you might like to stay a while. You can gently tap the like button if this feels like home. Subscribe if you'd like more stories, told softly, and ring the little bell not for noise, but so the next quiet night can find you again when you need it most. Now, let's drift. Tonight we're going to float up to that pale companion that's been watching over humanity since before we had words for moon or night or wonder. We'll discover why it holds one face toward us like a secret it's learned to keep, and why that secret took 4.5 billion years to perfect. You don't need to understand everything. Just rest your mind here and let curiosity do the listening. Picture this. You're standing outside on a clear night. The moon is full, bright enough to cast shadows on the grass. You see the dark patches, those ancient lava plains our ancestors called seas, though no water has ever pooled there. You see the bright highlands, the scattered craters like freckles on pale skin. This is the near side, the familiar face. Now, imagine walking around to the other side of Earth. Doesn't matter where, Tokyo, London, Rio, anywhere. Look up. That same face, those same seas, that same ancient pattern of light and shadow. Travel back in time 1,000 years, 10,000, a million. That face hasn't changed, not the orientation, not the side we see. Scientists call this phenomenon tidal locking. Though that name doesn't quite capture the poetry of it, doesn't quite capture the fact that the moon has been holding the same pose for longer than the Himalayas have existed, longer than the continents have held their current shapes. But tidal locking isn't magic. It's not coincidence. It's the patient work of gravity stretched out across geological time. And here's what makes it even stranger. The moon didn't always show us just one face. When you think about the moon, you probably picture it as permanent, ancient, unchanging. And in human terms, you'd be right. It's been that way for all of recorded history, for all of prehistory, for as long as anything resembling a human has looked up at the night sky. But the moon has a biography, a story that began in violence and settled into the quiet dance we see today. 4.5 billion years ago, back when the solar system was still young and chaotic, when planets were still finding their orbits and asteroid impacts were as common as summer rain, something happened to Earth, a Mars-sized planet which scientists now call Theia, after the Greek Titan who gave birth to the moon, goddess Selene, slammed into the early Earth at an angle. Not a head-on collision, but a glancing blow violent enough to be catastrophic, angled enough that both worlds didn't completely shatter. Imagine that for a moment. Imagine the sky filling with fire, the Earth's surface vaporizing, rock and metal and proto-oceans sprayed into space, forming a ring of superheated debris around what remained of Earth. And from that ring of wreckage and molten stone, the moon coalesced. In those first days, those first million years, the moon was different. It spun on its axis much faster than it does today. Picture it rotating every 6 to 8 hours, showing Earth all of its faces in less than a day. Both hemispheres got their turn in Earth's sky. Both sides bathe in sunlight and shadow in equal measure. The moon was also much, much closer. Some estimates put it at just 22,000 kilometers away, about 6% of its current distance. If you could stand on that early Earth and survive the hellish heat, the bombardment of asteroids, the toxic atmosphere, you'd see a moon that filled half the sky, massive, looming. So close you could see details we'd need telescopes to glimpse today. And it was moving, visibly moving, racing across the sky as both it and Earth spun in their frantic youthful orbits. But even then, even in that chaos, the forces that would lock it into place were already at work. Gravity was pulling at the rock, pulling at the molten interior, creating subtle bulges, tidal bulges in the moon's shape. Earth's gravity reached across that narrow gap of space and grabbed hold, and it never let go. Here's something that might surprise you. Tidal locking isn't rare. It's not some cosmic accident that happened to our moon alone. All across the solar system, moons have fallen into the same gravitational embrace with their planets. Io, Europa, Ganymede, Callisto, all four of Jupiter's largest moons show only one face to their giant host. Saturn's Titan does the same, Neptune's Triton. Even Pluto and its companion Charon are locked face to face forever, staring at each other across the darkness. Research shows that, given enough time, tidal locking is almost inevitable for any moon close enough to its planet. It's not special, it's just patient. But knowing that doesn't make it less wondrous, does it? Think about what this means. The moon has been showing Earth the same face for so long that entire mountain ranges have risen and eroded away on our planet's surface. Species have evolved, flourished, and gone extinct. Continents have drifted thousands of miles. And through all of that, through every ice age and warm period, through every meteor impact and volcanic eruption, the moon has kept its face turned toward us, like a faithful companion who never looks away. Our ancestors noticed this, of course. How could they not? Ancient cultures saw patterns in those shadows and bright plains. The Chinese saw a rabbit pounding medicine in a mortar. Europeans saw a man's face, the man in the moon. Some saw a woman, others a toad. The Maori of New Zealand saw a woman named Rona, who insulted the moon and was seized by it still clutching a tree. Every culture projected their stories onto that unchanging face, and it remained unchanging, patient constant, a canvas for human imagination, precisely because it never altered, never rotated away to show something new. But here's the question that should keep us awake. Why? Why does the moon show us only one face? What force in the universe is powerful enough to grab a world and say, "Turn this way forever"? The answer lies in something so subtle you'd never notice it in a human lifetime, something that works on timescales that make mountains look temporary. The answer is gravity, but not just the simple pull that keeps the moon in orbit. This is gravity with nuance, gravity with patience, gravity with the power to reach inside a world and rearrange it from the inside out. Scientists suggest that what locked the moon in place was the same force that lifts our oceans twice-a-day tidal force. But the version acting on the moon was far more dramatic than anything we experience on Earth. Because here's the thing about gravity, it gets weaker with distance. The side of the moon facing Earth feels Earth's pull more strongly than the far side does. That difference creates a stretch, a strain, a subtle deformation in the moon's shape. When the moon was still spinning, that bulge tried to stay aligned with Earth, but the moon's rotation kept dragging it out of alignment. This created friction, internal friction, rock grinding against rock deep inside the moon, generating heat, stealing energy from the moon's rotation. Slowly, so slowly that the change was invisible across millions of years, the moon's spin slowed down, and slowed down, and slowed down, until finally one face became permanently locked toward Earth, and the bulge aligned perfectly, and the friction ceased. The moon had found its position of lowest energy, the place where it could rest, and it's been resting there ever since. Have you ever wondered what it would be like to stand on the far side, that hidden hemisphere that no human eye saw directly until astronauts finally swung around it in 1968? It's not dark, that's a common misconception. We'll explore more deeply soon. It gets just as much sunlight as the near side, but it is different, profoundly different. The far side has almost none of those dark seas that dominate the face we know. Instead, it's heavily cratered ancient a landscape that looks almost alien compared to the moon we grew up with. Why, that's a story for later. But standing there on that far side, you'd see something no one on Earth has ever seen from the moon's surface, a sky without Earth. From the near side, Earth hangs in the sky, enormous and blue, always in the same position, rotating slowly through its day, while staying fixed in the moon's sky. It never rises, never sets, just hangs there, a swirling beacon of color in the black. But from the far side, Earth doesn't exist, not in the sky anyway, just stars and sun and the profound silence of a world where Earth's voice has never reached directly. The far side is truly alone, and it's been that way for billions of years. So, tonight when you look up at that familiar face, remember you're seeing the result of the longest embrace in the solar system. You're watching the final pose in a dance that began when our world was young and violent, a dance that slowed and settled and locked into place so gradually that even the rocks barely noticed. The moon shows us one side, not because it chose to, but because gravity chose for it, because time chose for it. Because in the mathematics of celestial mechanics, this was inevitable written into the equations before the first human ever looked up and wondered. And somehow, knowing that this familiar face was carved by forces beyond imagination, locked into place by the patient pull of our own world, somehow that makes it even more beautiful, doesn't it? The moon's loyalty isn't choice, it's physics. But in a universe of chaos and change, that constancy feels like a gift. But we've only just begun to understand how this happened. The mechanism is more intricate than simple gravity alone. There are forces at work, subtle, powerful, and visible, that reached inside the moon billions of years ago and haven't let go since. Let's drift deeper into those forces, into the grasp that binds the moon to Earth, into the physics of this eternal embrace. 4.5 billion years ago, there was no moon in Earth's sky. Just darkness stars, and a planet still finding its shape in the cosmic furnace of the early solar system. Then came the collision, not a gentle meeting, not a slow accumulation of dust, but violent, sudden, catastrophic, world-ending violence that somehow became world-creating. A protoplanet named Theia, roughly the size of Mars, had been wandering the inner solar system on an orbit that kept crossing Earth's path. For millions of years, maybe tens of millions, they missed each other. Near misses, close calls, gravitational tugs that altered both their trajectories slightly with each pass. But orbits are patient mathematics, and eventually the math aligned. Theia struck Earth at an oblique angle, traveling at roughly 15 kilometers per second. To put that in perspective, that's 40 times faster than a bullet. Fast enough that when rock meets rock at that speed, both behave like liquid. Like water droplets colliding in slow motion, except these droplets were made of iron and stone and measured thousands of kilometers across. The impact vaporized Theia's outer layers instantly. Earth's crust, where the collision hit, simply ceased to be solid. A massive plume of superheated rock, some of it vaporized into plasma, some liquefied, some shattered into fragments the size of mountains sprayed into space. If anything alive had existed on Earth, then it wouldn't have survived the first second. The entire planet rang like a struck bell. Shockwaves rippled through the mantle. The day-night cycle, if it existed at all, was obliterated by a sky full of fire. And from that fire, from that ring of debris orbiting a wounded Earth, the moon began to form. Scientists suggest this happened in stages. First, the larger chunks of debris, the pieces that were still semi-molten, still plastic enough to deform, began to collide and stick together. Gravity did what gravity does, best it pulled. Within perhaps a century, maybe less, most of the debris had accumulated into a single body. The moon was born hot, glowing its surface a magma ocean hundreds of kilometers deep. It didn't have a solid surface yet, just liquid rock slowly cooling, slowly crystallizing from the outside in. And it was spinning, fast. Research shows the newborn moon likely rotated once every 6 to 8 hours. Some models suggest even faster, perhaps as quick as 5 hours. Imagine that. A day on the early moon from sunrise to sunrise shorter than a single work shift. From Earth, if you could somehow stand on that molten hellish surface, you'd see the moon racing across the sky. It would rise arc overhead and set again in the span of a few hours, and it was huge. Staggeringly huge. The moon formed at a distance of roughly 22,000 kilometers from Earth. Today it orbits at an average distance of 384,000 kilometers. That's more than 17 times farther away. Do the math on apparent size, the early moon would have appeared about 17 times wider in the sky. Not just bigger, it would have dominated the entire horizon, stretching from east to west, a glowing disk that covered nearly 15 degrees of sky instead of the half degree we see today. Picture standing beneath that, a moon so large it felt close enough to touch, close enough to fall onto you. And both sides of that moon were visible from Earth. Over the course of its 6 to 8 hour day, you'd have seen every crater, every plane, every feature rotate into view and then disappear over the limb. The near side, the far side, all of it spinning past in endless succession. Back then there was no face we always see. There was just a spinning sphere showing everything hiding nothing. But even in those first days, the forces that would stop that spin were already at work. Earth's gravity wasn't pulling uniformly on the moon. The side facing Earth felt a stronger tug than the side facing away. This is called a tidal force, not because it involves water the early moon had none, but because it's the same force that lifts our oceans into bulges aligned with the moon's position in our sky. The moon being made of rock couldn't bulge as easily as water, but it could deform, slightly, slowly. The entire moon stretched into a slightly elongated shape like an egg, with its long axis pointing toward Earth. Now, here's the key: as the moon rotated, that bulge tried to stay aligned with Earth, but the moon's spin kept carrying it out of alignment. Imagine trying to hold a balloon stretched between your hands while someone spins it. The balloon wants to align with the pull, but the spin fights against it. Inside the moon, this created friction, rock grinding against rock, crystals sliding past each other in the still molten interior. And friction is a thief. It steals energy and converts it into heat. Slowly, over millions of years, the moon's rotation began to slow. Let's pause and consider the timescale here. This wasn't a sudden stop. This wasn't something you could watch happen even if you lived 1,000 human lifetimes. Scientists estimate it took between 1 and 2 billion years for the moon to become tidally locked. That's roughly a quarter to half the age of the solar system. That's longer than multicellular life has existed on Earth, longer than oxygen has been abundant in our atmosphere. 1 billion years, with a B. During that time, the moon's day lengthened from 6 hours to 12, then 24, then a week, then 2 weeks, then a month, until finally one day, and no one was there to mark it. No one was there to notice the moon's rotational period matched its orbital period exactly. 27.3 days to spin once on its axis. 27.3 days to circle Earth once. Locked. The bulge aligned permanently with Earth. The friction stopped. The moon settled into its lowest energy state, the configuration where gravity's tug and the moon's shape finally agreed. And it's been that way ever since. For the last 3 billion years, give or take, the moon has shown Earth the same face, unchanging constant, locked in an embrace that will likely last until the sun itself dies. But why did it lock at all? Why didn't the moon just keep spinning forever? The answer comes down to something called tidal dissipation. When the moon's interior flexed and deformed with each rotation, that friction didn't just slow the moon down, it converted rotational energy into heat. The moon was literally heating itself up by spinning, losing orbital energy in the process. Think of it like rubbing your hands together on a cold day. The friction creates warmth. Your hands slow down. Energy is dissipated as heat. The moon did the same thing, except instead of hands, it was an entire world. And instead of seconds, it took eons. Eventually, inevitably, all that rotational energy got used up. The moon stopped spinning relative to Earth, and the heating stopped. Equilibrium was reached. This is why tidal locking is so common in the solar system. Given enough time and close enough proximity, every moon will lock to its planet. It's not special. It's thermodynamics. It's the universe seeking the lowest energy state, the way water seeks the lowest point in a landscape. Jupiter's moon, Io, for instance, became tidally locked relatively quickly within just a few million years, because it orbits so close to Jupiter that the tidal forces are enormous. Jupiter's gravity kneads Io like dough, generating so much internal friction that Io is the most volcanically active body in the solar system. Over 400 active volcanoes, erupting constantly, all powered by tidal heating. Our moon never had that level of tidal stress. It was farther from Earth, smaller, less intensely squeezed. Its locking was gentler, slower, quieter, but just as inevitable. Here's something most people don't realize. The moon we see today is not the moon that locked into place 3 billion years ago. After the locking occurred, the moon didn't just freeze in time. It continued to evolve. Asteroids and comets continued to bombard its surface, carving out craters, fracturing bedrock, creating the scarred landscape we see today. Some of those impacts were recent geologically speaking. The crater Tycho, that bright ray system visible near the moon's south pole, formed only 108 million years ago. Dinosaurs were already walking Earth when that asteroid struck. Copernicus crater, another prominent feature, is even younger, just 800 million years old. That's recent enough that complex life already existed in Earth's oceans when it formed. But the moon's orientation never changed. Tycho formed on the near side, and it stayed on the near side. The moon may be battered, may be ancient, may be covered in the scars of 4 billion years of cosmic bombardment, but it's been showing us the same face through all of it. That's the stability tidal locking provides. Once locked, a moon doesn't just randomly start spinning again. It would take another massive collision, another Theia-scale impact to break that lock. And the odds of that happening are vanishingly small. So, what was the early moon like back when it still spun? Back before the lock engaged? Imagine standing on that primordial surface if such a thing were possible. If you could survive the heat and the radiation and the constant bombardment of asteroids. You'd see Earth wheeling overhead, massive and glowing red, from its own volcanism rotating once every 6 hours, because Earth too was spinning much faster back then. The sun would rise and set every 6 to 8 hours. Not the slow, stately sunrise we're used to, but a rapid transition from day to night and back again. The landscape would heat and cool in rapid cycles, expanding and contracting, cracking and settling. And every few hours, Earth would rotate through a full day-night cycle in the moon's sky. You'd see continents, though. They looked nothing like today's continents. You'd see the glint of magma oceans. You'd see storm systems swirling in the thick, toxic atmosphere. It would have been beautiful. Alien. Nothing like the serene, locked configuration we have today. But that era ended. Slowly, imperceptibly, gravity's patient hand slowed the moon's spin, until the dance became a held pose, until motion became stillness, until chaos settled into the quiet we now take for granted. There's a kind of poetry in that, isn't there? The universe began in violence, stars exploding, planets colliding, worlds forming from wreckage. And yet, given enough time, it finds stillness, it finds balance. It finds a way to turn chaos into something almost gentle. The moon's locking is a reminder that even in a violent universe, patience wins. Friction wins, time wins. And what it creates, what emerges from a billion years of slow deceleration, is constancy. A faithful face in the night sky. A companion that never looks away. But the story doesn't end with the lock. Because even now, even as the moon shows us the same face it's shown for 3 billion years, forces are still at work. The dance isn't over. It's just evolved. The moon is still moving, still changing, still responding to Earth's pull in ways that will reshape both worlds over the eons to come. And that movement, that slow, inevitable drift begins with understanding the grip that holds them together, the invisible hand that locked the moon in the first place, and continues to shape its fate. Right now, as you're listening to this, the ocean nearest to the moon is rising. Not dramatically, not suddenly, but rising nonetheless, pulled upward by an invisible hand reaching across 250,000 miles of empty space. And on the opposite side of Earth, impossibly, the ocean is rising there too. Two bulges, one facing the moon, one facing away, both lifting simultaneously as if the planet is being stretched like taffy in slow motion. This is the moon's grip on Earth, gentle, constant, undeniable. And here's the part that matters. Earth does the same thing back to the moon, except Earth's grip is 80 times stronger, and instead of lifting water, it's lifting rock, solid rock, deforming like clay in invisible hands. Gravity isn't just the force that keeps the moon in orbit. It's more intimate than that, more invasive. Gravity reaches inside both worlds and reshapes them from within, creating bulges and stresses that have been pulling at the moon's interior for billions of years. This is what locked the moon in place. This is the gentle grasp that never lets go. Let's understand how. When we think about gravity, most of us picture it as a simple pull. One object attracts another, and that's that. The moon pulls on. Earth pulls on the moon, and they stay in orbit around their common center of mass. But gravity is more nuanced than that. It doesn't pull uniformly. The strength of gravity depends on distance, and it falls off rapidly. Specifically, it follows an inverse square law. Double the distance, and gravity becomes 4 times weaker. Now, the moon is big, really big. Its diameter is 3,474 kilometers. That means the side of the moon facing Earth is about 3,500 kilometers closer to Earth than the far side is. 3,500 kilometers doesn't sound like much compared to the 250,000-mile gap between Earth and Moon. It's only about 1% of the total distance. But gravity is sensitive. That 1% difference in distance creates a measurable difference in gravitational pull. The near side of the moon feels Earth's gravity more strongly than the far side does. And that difference, that gradient in gravitational strength, is what scientists call a tidal force. Here's how it works. Imagine the moon as a collection of particles all being pulled toward Earth. The particles on the near side are pulled harder than the particles at the center, which are pulled harder than the particles on the far side. The result? The moon gets stretched, elongated, deformed into a slightly egg-shaped object with its long axis pointing toward Earth. It's not a huge deformation. The solid rock of the moon only bulges outward by about 20 meters on each side, barely noticeable if you were standing on the surface. But 20 meters of rock displacement across an entire world represents an enormous amount of stored energy. Now, when the moon was still spinning freely, this bulge tried to stay aligned with Earth. But the moon's rotation kept dragging it out of alignment. The bulge would form on the side facing Earth, but then the moon would rotate, carrying that bulge away from the Earth-facing direction. Gravity would pull it back into alignment. The moon would rotate it away again, back and forth, over and over, millions of times per year, billions of times over the eons. And each time the bulge shifted, the moon's interior had to deform. Rock had to flex. Crystals had to slide past each other. And that created friction, internal friction, that converted the moon's rotational energy into heat. Think of it like bending a paperclip back and forth. The first few bends are easy, but keep bending it in the same spot and the metal heats up. That's friction at work motion being converted into thermal energy. Eventually, the paperclip breaks or becomes too weak to bend further. The moon did something similar, except instead of breaking, it stopped rotating. It found the position where the bulge aligned permanently with Earth, where no more bending was necessary, where the friction ceased. That position is tidal locking. The moon's day became equal to its orbital period. The same side faces Earth always. The bulge stays put. The system reached equilibrium. And it's been in equilibrium for roughly 3 billion years. But here's what makes this even more fascinating. Earth experiences the same tidal forces from the moon. In fact, the moon's tidal effect on Earth is far more obvious because we have ocean's liquid water that can flow and bulge much more easily than solid rock. Twice a day the ocean rises, high tide. Twice a day it falls, low tide. This isn't because water is being created or destroyed. It's because the water is being pulled into two bulges, one on the side facing the moon, one on the opposite side. The bulge facing the moon makes intuitive sense. The moon pulls harder on the water nearest to it, lifting it upward. But why does the water on the far side also bulge outward? This confuses a lot of people. It seems like the water on the far side should be pulled less, not more. And that's true, it is pulled less. But here's the key: the solid Earth beneath that water is also being pulled toward the moon, and it's being pulled more strongly than the far side water is. So the Earth gets pulled away from the water on the far side, leaving that water behind, creating a bulge there too. It's not that the far side water is being pushed outward, it's that the Earth is being pulled away from it. The result looks the same, a bulge, but the mechanism is subtly different. Now, Earth also has a solid body tide, though we don't notice it as easily. The ground beneath your feet rises and falls by about 30 centimeters twice a day as Earth's rocky crust deforms in response to the moon's pull. 30 centimeters, about a foot. The ground is breathing, flexing, moving up and down, and you never feel it because it's so gradual, so smooth, so synchronized with your own motion through space. But instruments can measure it. GPS satellites detect it. Seismometers record it. The Earth is not rigid. It's elastic, deformable, constantly responding to the moon's gravitational whisper. And 4.5 billion years ago, when the moon was much closer and the tidal forces were much stronger, these deformations were far more dramatic. Scientists estimate that the early Earth's crust may have flexed by several meters with each tidal cycle. The ground would have visibly risen and fallen, creating stresses that fractured rock, generated heat, and contributed to the planet's intense volcanic activity. The moon, being smaller and closer to Earth, experienced even more intense tidal stresses. Its surface may have deformed by hundreds of meters in those early days, enough to keep the interior partially molten enough to create constant internal friction, enough to slow its rotation within a geologically short time. Let's talk numbers for a moment, because numbers make the invisible visible. The tidal force exerted by Earth on the moon is proportional to the mass of Earth divided by the cube of the distance between them. Earth's mass is about 81 times the moon's mass. But when the moon was at 22,000 kilometers distance instead of 384,000, that distance factor becomes huge. Specifically, the tidal force was about 384,000 over 22,000 cube times stronger. That's 17 cubed. That's over 5,000 times stronger than today. 5,000 times. Let that sink in. The early moon wasn't just being gently tugged. It was being wrenched, kneaded, squeezed like dough in a cosmic fist. The stresses were so intense that the moon's interior stayed partially molten for hundreds of millions of years longer than it otherwise would have, delaying the formation of a fully solid mantle. This intense tidal heating also explains why the moon differentiated so thoroughly, why its dense iron core sank to the center, and its lighter materials floated to the surface. The constant churning, the internal convection driven by tidal friction, allowed materials to separate by density more efficiently than they could have through simple gravitational settling alone. But the tidal forces didn't just heat the moon. They also transferred angular momentum, the rotational energy of the moon's spin, into orbital energy. As the moon's rotation slowed, that lost energy had to go somewhere. It went into the moon's orbit, causing the moon to spiral outward away from Earth. This is still happening today. The moon is currently receding from Earth at a rate of about 3.8 centimeters per year. That's roughly the speed your fingernails grow. Slow. Imperceptible in a human lifetime, but measurable with laser-ranging experiments where we bounce light off reflectors left on the moon by Apollo astronauts. Over billions of years, that slow drift adds up. The moon has moved from 22,000 kilometers to 384,000 kilometers, an increase of more than 17 times. And it's still drifting. Eventually, billions of years from now, the moon will be so far away that its tidal effect on Earth will be negligible. But we'll explore that distant future later. For now, let's stay with the mechanism itself. Tidal locking isn't unique to the Earth-Moon system. It's a universal process that happens wherever a moon orbits close enough to its planet for tidal forces to dominate over the moon's rotational inertia. Jupiter's moon, Io, for example, is tidally locked. So, are Europa Ganymede and Callisto, all four of Jupiter's large moons. Saturn's Titan is locked. Neptune's Triton is locked. Even Pluto and its moon Charon are mutually tidally locked, meaning both bodies always show the same face to each other. The closer a moon orbits, the faster tidal locking occurs. Io, orbiting just 422,000 kilometers from Jupiter's center, locked within a few million years. Callisto, orbiting at nearly 2 million kilometers, took much longer, perhaps hundreds of millions of years, but still locked eventually. Our moon, orbiting at an intermediate distance with intermediate tidal forces, took 1 to 2 billion years. Not fast, not slow, just the patient arithmetic of gravity doing its work. There's a common misconception worth addressing here. Some people think tidal locking means the moon doesn't rotate at all, that it's sitting still in space, frozen in place. That's not correct. The moon rotates once per orbit, once every 27.3 days. If it didn't rotate, we'd see all sides of it as it orbited Earth, the way we see all sides of a space station as it circles the planet. Tidal locking means the rotation period equals the orbital period, synchronous rotation. One face toward Earth always, but the moon is still spinning, just very, very slowly. So slowly that one lunar day lasts an entire Earth month. Imagine that. Sunrise on the moon. The sun creeps above the horizon, takes 2 weeks to arc across the sky, sets 2 weeks later. Then 2 weeks of night, then sunrise again. A month-long day-night cycle, slow and stately and utterly alien to our experience. And through all of it, Earth hangs in the sky. If you're on the near side, never rising, never setting, just rotating through its own day-night cycle every 24 hours while remaining fixed in position. A blue and white ornament suspended in the black, unchanging in placement, ever-changing in appearance. From the far side, Earth never appears at all. Just the sun wheeling slowly across the sky, and stars that never move except for their own slow drift across the seasons. So, when we ask why the moon shows us only one face, the answer comes down to, this gravity is patient and gravity is thorough. It reached into the moon billions of years ago and found the bulges, the asymmetries, the slight variations in density and shape. It pulled on those irregularities, creating friction, stealing rotational energy, slowing the spin. And it never stopped pulling. Not for 1 billion years, not for 2 billion, not until the moon's rotation matched its orbit, until the same face turned toward Earth, always, until the system found the lowest energy state and settled there. That's the gentle grasp that binds them. Not violent, not sudden, just persistent. A pull that spans centuries, millennia, eons. A cosmic embrace that turned a spinning world into a faithful companion, forever watching, forever held. But the story of how this lock became permanent, how the moon transitioned from a spinning body to a locked one that requires us to look deeper into time, into the slow surrender of rotation to gravity's will. There was a moment, though, no one witnessed it, though it passed unmarked by any consciousness in the universe, when the moon completed its final free rotation. One last spin, one last time, showing Earth all of its faces in succession. And then, imperceptibly, the rotation slowed just enough that one face began to linger, to stay, to lock into place. It didn't happen in a day. It didn't happen in 1 million days. It took somewhere between 1 and 2 billion years for the moon to surrender its spin completely. And the weapon that forced that surrender wasn't violence. It was friction, patient, invisible, relentless friction. Let's understand how a world loses its ability to turn. Imagine holding a ball of clay in your hands. Now squeeze it gently, then release. Squeeze again, release, over and over. What happens? The clay heats up. You can feel it warming in your palms. That warmth is friction, the clay's internal structure, resisting the deformation and particles sliding past each other, molecular bonds flexing and releasing, motion being converted into heat. Now, imagine doing that for 1 billion years, not with clay, but with rock, not with your hands, but with gravity, not squeezing randomly, but with a precise rhythm tied to the moon's rotation. That's what Earth's gravity did to the moon, and that's what finally stopped it from spinning. The mechanism is called tidal friction. Though the name is somewhat misleading, it's not friction in the traditional sense, not two surfaces rubbing together. It's internal friction, deformation friction. The resistance of solid matter to being repeatedly stretched and released. Here's how it worked. As the moon rotated, Earth's gravity created that tidal bulge we discussed, the elongation pointing toward Earth. But the moon's rotation kept trying to carry that bulge away from the Earth-facing direction. Imagine the bulge forming on the side closest to Earth. Now the moon rotates a few degrees. The bulge wants to stay aligned with Earth, but the moon's solid structure is carrying it sideways. Gravity pulls it back. The moon's rotation drags it forward. Pull, drag, pull, drag. Inside the moon, this created shear stress. Layers of rock sliding past each other at infinitesimally slow speeds. Crystals deforming, grain boundaries shifting. And every time the internal structure deformed, a tiny amount of energy was converted from motion into heat. Tiny. Almost immeasurably small per rotation. But the moon was rotating thousands of times per year in those early days. Millions of times per millennium. Billions of times per billion years. And each rotation stole a little more energy. Each deformation converted a little more spin into warmth. The moon was quite literally friction heated from within by its own rotation in Earth's gravitational field. Scientists estimate that at its peak, this tidal heating may have contributed significantly to keeping the moon's interior molten. Not as much as radioactive decay that was still the primary heat source, but enough to matter. Enough to delay the moon's cooling by hundreds of millions of years. Think about that. The moon was heating itself up by spinning. The faster it spun, the more it heated. And the more it heated, the more easily its interior could deform, which created more friction, which stole more rotational energy. It was a feedback loop, a self-reinforcing process. The moon's spin was eating itself from the inside out. Over time, vast amounts of time, the rotation slowed. The moon's day lengthened from 6 hours to 8, then 10, then 12. Each additional hour meant the tidal bulge had more time to align with Earth before being dragged away again. Less deformation per rotation, less friction, less heating. But the process didn't stop, it just slowed down. Like a spinning top gradually coming to rest, wobbling less and less, the moon's rotation approached synchronization with its orbit. Here's where the mathematics becomes beautiful. The moon's orbital period, the time it takes to circle Earth once, was also changing during this process. As the moon's rotation slowed, the energy it lost had to go somewhere. Conservation of angular momentum demanded it. That energy went into the moon's orbit. Specifically, it increased the moon's orbital angular momentum, which pushed the moon farther from Earth. The moon began to spiral outward, slowly, steadily gaining altitude as it lost spin. This might seem counterintuitive. You'd think losing energy would make the moon fall closer to Earth, not move away. But orbital mechanics is strange. When you add energy to an orbit, the orbiting body moves to a higher, slower orbit. The moon slowed its spin, but also slowed its orbital speed, settling into a larger orbit farther from Earth. The numbers are precise. For every bit of rotational energy the moon lost to tidal friction, A corresponding amount appeared as orbital energy. The books balanced. The universe kept its accounting straight. And as the moon moved farther away, Earth's tidal grip on it weakened. The forces that created the friction became less intense. The process of slowing down itself slowed down. Eventually, after 1 to 2 billion years, the moon reached a distance and rotation rate where its spin period exactly matched its orbital period. 27.3 days to rotate once. 27.3 days to orbit Earth once. Perfect synchronization. The tidal bulge aligned permanently with Earth. No more dragging, no more deformation, no more friction. The moon had surrendered its spin, and the universe rewarded that surrender with equilibrium. But why did it take so long? Why 1 to 2 billion years instead of, say, a few million? The answer lies in the moon's size and composition. The moon is solid rock, not a gas giant or ice ball. Rock is stiff. It resists deformation. The amount of energy dissipated per rotation was tiny, absolutely minuscule compared to the moon's total rotational energy. To put this in perspective, the moon's rotational kinetic energy in those early days was enormous. Scientists estimated it roughly 10 to the power of 28 joules. That's a 1 followed by 28 zeros. For comparison, the total energy humanity uses in a year is about 10 to the power of 20 joules. The moon's spin contained 100 million years' worth of humanity's current energy consumption. Dissipating that much energy through internal friction at the rate of perhaps a few terawatts comparable to Earth's current tidal dissipation takes a very, very long time. The math works out to roughly 1 billion years, give or take a factor of 2, depending on the moon's internal structure and the exact distance from Earth. So, the timeline makes sense. It wasn't fast, but it wasn't infinitely slow either. Just the patient arithmetic of thermodynamics playing out across geological time. Now, here's something fascinating. The process wasn't perfectly smooth. There may have been periods where the slowing accelerated or decelerated depending on the moon's internal structure at the time. Early in the moon's history, when much of its interior was still molten or partially molten, the rock could deform more easily. More deformation means more friction, means faster energy. Dissipation means faster spin down. Later, as the interior solidified, the moon became stiffer. Less deformation per rotation. Less friction. The slowing process would have decelerated somewhat, taking longer in those later stages than in the early molten period. There's also evidence that the moon didn't lock smoothly into its current orientation on the first try. Some researchers suggest the moon may have passed through several quasi-stable configurations, temporary locks that held for millions of years before breaking and relocking in a slightly different orientation. This could have happened if the moon's mass distribution wasn't perfectly symmetrical. If one side was slightly denser than the other, Earth's gravity would have pulled harder on that denser side, creating a preferred orientation. But if the difference was small, the lock might have been weak enough that orbital perturbations or impacts could have broken it temporarily, allowing the moon to shift to a new locked orientation that better matched its evolving mass distribution. Eventually, though, the moon found its final configuration, the one we see today. And once locked, it stayed locked. For 3 billion years and counting. Let's compare this to other moons in the solar system to see if our moon's experience was typical or unusual. Jupiter's moon, Io, locked far faster than our moon, probably within just a few million years of its formation. Why? Because Io orbits incredibly close to Jupiter, only 422,000 kilometers from Jupiter's center, which is barely farther than our moon's current distance from Earth. But Jupiter is 318 times more massive than Earth, so the tidal forces are immense. Io experiences so much tidal friction that its interior is still molten today billions of years after formation. It has over 400 active volcanoes. Its surface is constantly being resurfaced by lava flows. Tidal heating, not radioactive decay, is the primary heat source keeping Io's interior liquid. That's how powerful tidal forces can be when you're close to a massive planet. Io didn't gradually slow to a stop over 1 billion years. It locked almost immediately and has been pumping out tidal heat ever since. At the other extreme, consider Saturn's moon, Iapetus. It orbits far from Saturn, 3.5 million kilometers, and locked relatively late in solar system history. Scientists estimate it may have taken hundreds of millions of years for Iapetus to lock and only managed it at all because Saturn is so massive that even at that great distance, tidal forces were sufficient. Our moon falls in the middle, not too close, not too far, locked at a moderate pace by moderate tidal forces. Just another moon following the universal script that gravity writes for all satellites. But there's a subtlety here that most people miss. Tidal locking doesn't just depend on the strength of tidal forces. It also depends on the moon's shape and internal structure. If the moon were perfectly spherical with a perfectly uniform density, tidal locking would take longer, perhaps much longer, because there would be no preferred orientation. Earth's gravity would pull equally on all sides, and the moon could lock in any orientation by chance. But the moon isn't perfectly spherical. It's slightly elongated with a mass concentration, a mascon, beneath the near side. The near side is measurably more massive than the far side, creating an asymmetry that Earth's gravity could latch onto. Scientists believe this asymmetry may have been created by the tidal forces themselves. As the moon's interior was still cooling and solidifying, the constant tidal stress may have preferentially concentrated denser materials on the near side, creating the very asymmetry that would later lock the moon in place. In other words, the tidal forces sculpted the moon's interior into a shape that made tidal locking easier. The process created the conditions for its own completion, self-organizing, self-reinforcing, the universe finding the most efficient path to equilibrium. There's a common mistake people make when thinking about tidal locking. They imagine it as the moon gradually braking to a stop, like a car coasting to a halt. But that's not quite right. The moon didn't stop rotating. It's still rotating just very slowly once per orbit. What changed was the relationship between its rotation and its orbital motion. They synchronized. Think of it like a dancer spinning while also circling a partner. If the spin rate matches the circling rate, the dancer faces their partner continuously without ever turning away. That's tidal locking. The dancer is still spinning, still moving. But from the partner's perspective, they always see the same face. The moon is that dancer. Earth is the partner. And the dance has been synchronized for 3 billion years. So, when we ask how the moon lost its spin, the answer is it didn't lose it. It transformed it. The rapid independent rotation of the early moon, 6 to 8 hours per spin, gradually morphed into a slow synchronized rotation locked to the orbital period. The energy of that original spin didn't vanish. Some converted to heat warming the moon's interior. Some converted to orbital energy pushing the moon farther from Earth. Some dissipated into space as infrared radiation from the moon's cooling surface. But the pattern of that spin, the angular momentum is still there, encoded in the moon's orbit and rotation, conserved, transformed, redistributed across the Earth-Moon system. This is what makes tidal locking so elegant. It's not destruction. It's reorganization. Chaos settling into order. A high-energy state transitioning to a low-energy state following the arrow of entropy, but creating structure and stability in the process. The moon surrendered its free spin, and in exchange it gained permanence, a fixed relationship with Earth, a guaranteed view of the blue planet that pulled it into position and never let go. But that view, that eternal gaze at Earth, comes with a cost. The moon showed us something, and in doing so, hid something else. A whole hemisphere we've never seen from Earth's surface. A hidden face with its own story, its own scars, its own mysteries. For most of human history, half of the moon was a complete mystery, a blank space in our understanding, an entire hemisphere that no eye had ever glimpsed, no instrument had ever measured, no imagination could accurately conjure. We called it the dark side of the moon. And that name, poetic, evocative, slightly ominous, stuck in the cultural imagination. Pink Floyd made an album about it in 1973, one of the best-selling records of all time. Science fiction writers set their stories there. Conspiracy theorists imagined alien bases hidden on that perpetually shadowed surface. But here's the thing, the dark side of the moon isn't dark. It never was. It's one of the most persistent misconceptions in popular astronomy, and it's time we set the record straight. The far side of the moon gets just as much sunlight as the near side. Always has, always will. Let's start with the terminology because words matter. When astronomers talk about the moon's hidden hemisphere, they don't call it the dark side. They call it the far side. Far, not dark. The distinction is crucial. Dark implies absence of light, shadow, eternal night. But the far side of the moon spends half of each lunar month, about 2 weeks, bathed in full sunlight. During what we call a new moon, from Earth's perspective, the far side is experiencing lunar noon, full daylight, bright enough to cast sharp shadows across its ancient cratered surface. The confusion comes from conflating two different meanings of dark. We use dark to mean both unlit and unknown. The far side is unknown, or at least it was until recently, but it's not unlit. It's only dark in the sense that it was hidden from our view, mysterious, unexplored. But language shapes perception. When people hear dark side of the moon, many genuinely believe that hemisphere never sees sunlight, that it's locked in permanent shadow, frozen lifeless in a way the near side isn't. That's simply not how it works. Think about it this way. The moon orbits Earth once every 27.3 days. During that orbit, the sun illuminates the moon from different angles, just like it illuminates Earth from different angles as we orbit the sun. When the moon is between Earth and the sun, what we call a new moon, the far side faces the sun and is fully lit. The near side, the side facing us, is in shadow. We can't see the moon at all from Earth because we're looking at its dark side. And in this case, dark genuinely means unlit. 2 weeks later, the moon is on the opposite side of Earth. Now the near side faces the sun and is fully lit. We call this a full moon, and at this moment, the far side is experiencing lunar night. It's dark in the literal sense, no sunlight, just starlight and the faint glow of reflected light from Earth, which the far side never sees. The far side gets its day. It gets its night. It experiences the full cycle of lunar illumination, just like the near side does. The only difference is that we don't see it happening. So, where did the dark side terminology come from? The phrase predates Pink Floyd by decades, possibly centuries. Its origins are murky, but it likely comes from maritime language. Sailors referred to uncharted waters as dark in the sense of unknown, unmapped, dangerous. The far side of the moon was dark in that metaphorical sense, a blank on our maps, a mystery wrapped in silence. The phrase gained prominence in the space age. In 1959, when the Soviet Luna 3 spacecraft became the first human-made object to photograph the far side, newspapers and magazines around the world ran headlines about the dark side of the moon finally revealed. They meant hidden, but readers interpreted dark literally. Pink Floyd's 1973 album cemented the phrase in popular culture. The album isn't really about the moon. It's a meditation on madness pressure and the human psyche. But the title evoked mystery and shadow in a way that resonated deeply. Millions of people who'd never thought much about lunar astronomy suddenly had dark side of the moon in their vocabulary. And misconceptions have a way of taking root and growing wild. Here's what the far side actually looks like. In 1959, when Luna 3's grainy, low-resolution images came back, scientists were shocked. Not because the far side was alien or artificial or hiding anything unusual, but because it looked so different from the near side. The near side of the moon is dominated by dark, smooth plains called maria, Latin for seas, though they are not actually water. These maria are ancient lava flows that filled in massive impact basins billions of years ago. They give the near side its distinctive patterns, the man in the moon or rabbit pounding rice that cultures have seen for millennia. But the far side has almost no Maria. It's heavily cratered, bright, rough, ancient looking. It looks more like what we'd imagine the moon should look like, covered in impact scars untouched by volcanic resurfacing. Why the difference? That question puzzled scientists for decades, and we still don't have a complete answer. But the leading theory has to do with the moon's crust thickness. Scientists believe the far side's crust is significantly thicker than the near side's, about 50 to 60 kilometers thick, compared to 30 to 40 kilometers on the near side. When large asteroids struck the moon in its early history, the impacts on the near side could fracture through that thinner crust, allowing magma from below to well up and flood the impact basins. The far side's thicker crust resisted fracturing, so the impact basins stayed dry, unfilled, their original shape preserved. But why is the crust thicker on one side? That's a deeper mystery, possibly related to tidal forces from Earth during the moon's formation, possibly related to the way the moon cooled and solidified. The research is ongoing. The first humans to actually see the far side weren't scientists on Earth watching fuzzy photographs. They were astronauts aboard Apollo 8 in December 1968. Frank Borman, Jim Lovell, and William Anders became the first people to swing around the moon and glimpse what no human eye had ever seen directly. Anders later described it as a different thing altogether from the near side, more rugged, more alien, a landscape that felt genuinely untouched by anything except time and impacts. There's a famous photograph from that mission, not of the far side, but taken while viewing the far side. It shows Earth rising above the lunar horizon, a delicate blue marble floating in the black void above the moon's stark gray landscape. That image, Earthrise, became one of the most iconic photographs of the 20th century. But what's often forgotten is where the astronauts were when they took it. They were looking at the far side. Earth doesn't rise or set from the near side, it just hangs there fixed in position. Only from the far side or from the limb regions between near and far can you see Earth appear above the horizon. The astronauts captured that moment of transition, that boundary between the hemisphere that knows Earth and the hemisphere that doesn't. Let's address another common misconception. Some people believe the far side is tidally locked to face away from Earth deliberately, as if the moon chose to hide that side from us. As if there's something special about the far side that the universe wanted to keep secret. This is backwards. Tidal locking doesn't care which side faces which direction. There's nothing inherently special about the hemisphere that faces Earth versus the one that doesn't. The lock could have settled with any orientation whichever one happened to have. The right mass distribution to create a stable configuration happened to be the one that locked. In other words, the division into near side and far side is arbitrary from the moon's perspective. It's only meaningful from our perspective on Earth. If the moon had locked with a different face toward us, we'd be calling that one the near side and wondering about the unseen far side that happened to be what we currently call the near side. The moon doesn't hide anything deliberately. It's just locked in whatever orientation gravity settled it into billions of years ago. We're the ones who assign meaning to that division, near versus far, familiar versus mysterious, known versus dark. There's also a persistent belief that the far side is colder than the near side because it never sees sunlight. But temperature on the moon isn't determined by which side faces Earth. It's determined by whether the sun is currently illuminating that particular spot. During lunar day, those 2 weeks of continuous sunlight, surface temperatures on both near and far sides can reach about 127 degrees Celsius. That's 260 Fahrenheit, hot enough to boil water, if any existed. During lunar night, 2 weeks of continuous darkness, temperatures plummet to around negative 173 degrees Celsius, negative 280 Fahrenheit. Cold enough to freeze carbon dioxide, if any existed, in the thin wisps of the lunar exosphere. The far side gets just as hot and just as cold as the near side. The only thermal difference is that the near side receives a tiny amount of infrared radiation from Earth. Earth glows in the infrared from its own heat, but that's a negligible effect, raising temperatures by maybe a degree or two at most. In every way that matters, the far side and near side experience the same solar environment, same sunlight, same darkness, same temperature extremes. The only real difference is what they see when they look up. From the near side, Earth hangs in the sky, always, a massive, brilliant, ever-changing ornament that rotates through its day-night cycle, but never rises or sets. Astronauts on the near side during Apollo missions could always look up and see home, a comforting, beautiful reminder of where they came from. But from the far side, Earth doesn't exist in the sky at all. Just stars. The sun wheeling slowly overhead during the 2-week day. Venus sometimes bright enough to cast shadows. Mars as a reddish point. Jupiter visible to the naked eye on a clear night. But no Earth, no blue marble, no clouds, no oceans, no continents. The far side is truly alone, cut off not just from our view, but from Earth's presence entirely. There's something profound about that. The far side has never seen Earth, not once in 4.5 billion years. Lava erupted there billions of years ago and cooled without ever having reflected Earthlight. Asteroids struck and threw up ejecta that settled back down without Earth's gravity perturbing the trajectories. Moonquakes have shaken the surface, and no seismometer on the far side has ever detected the subtle tidal stress from Earth's pull, not because it doesn't exist, but because they're too far apart in seismic networks to triangulate it. The far side is an Earth-less zone, a place where our planet has never been part of the landscape, never colored the sky, never been available for navigation or timekeeping or inspiration. And yet, despite all this, the far side has now been visited. Not by humans, no one has walked on the far side yet, but by robotic explorers. In January 2019, China's Chang'e 4 mission successfully landed on the far side, the first spacecraft ever to do so. Why did it take until 2019? Because landing on the far side is genuinely harder than landing on the near side. Not because of darkness or cold or anything physical about the terrain, but because of communication. When you're on the near side, you can talk directly to Earth. Radio signals travel straight from spacecraft to ground stations. But on the far side, the entire bulk of the moon blocks your signal. You're cut off, isolated. Any spacecraft on the far side needs a relay satellite positioned at a Lagrange point, where it can see both Earth and the far side simultaneously acting as a communication bridge. China placed a relay satellite Kuekiao at the Earth-Moon, L2 Lagrange point before sending Chang'e 4 to the surface. And it worked. The rover sent back images data measurements. It studied the composition of the lunar soil. It grew seeds in a small biosphere experiment they sprouted briefly before dying in the harsh cold of lunar night. But the most important thing it did was prove that the far side is accessible, that the dark side isn't forbidden, isn't impossible, isn't hiding anything we can't study. It's just far, just hidden from our direct view, just a hemisphere of the moon like any other hemisphere following the same laws of physics, experiencing the same sunlight and starlight, quietly enduring the eons. So, when you hear someone mention the dark side of the moon, you'll know what they really mean. They mean the far side, the hidden side, the hemisphere we couldn't see for most of human history and still can't see from Earth. But you'll also know it's not dark, not in any literal sense. It's as bright as the side we know, sometimes brighter when Earth is between it and the sun and it basks in full solar illumination, while we see only a thin crescent. The moon doesn't have a dark side, it has a hidden side. And hiding isn't the same as darkness. Perhaps that's a useful lesson beyond astronomy. How often do we call something dark simply because we can't see it? How often do we mistake unknown for unknowable or hidden for sinister? The far side of the moon was a mystery for billions of years. But once we built the tools to look, once we sent our cameras and rovers and radio relays, we found it wasn't dark at all. Just different. Just waiting to be understood. And understanding doesn't diminish mystery. If anything, it deepens it. Because now we can ask better questions. Why is the crust thicker there? What does the chemical composition tell us about the moon's formation? How might we use the far side as a site for future radio telescopes, shielded from Earth's electromagnetic noise? The answers to those questions won't make the far side less wondrous. They'll make it more real, more a part of our expanding circle of knowledge, less a placeholder for imagination, and more a place we might someday walk, study, perhaps even inhabit. But before we get too far ahead, before we start building lunar bases and radio arrays on that hidden hemisphere, there's something else happening between Earth and Moon that deserves our attention. Something slow and inevitable, something that's been quietly reshaping their relationship for billions of years and will continue long after we're gone. Every night when you look up at the moon, it's a little bit farther away than it was the night before. Not much. Not enough to see with your eyes, not enough to measure with a ruler, but farther nonetheless, 3.8 centimeters. That's how much distance the moon gains each year. About 1.5 inches, the same rate your fingernails grow. The moon is leaving us, slowly, imperceptibly, but inevitably. And it's been leaving for billions of years. In fact, the moon has already traveled more than 300,000 kilometers away from where it started. That's like moving from New York to Los Angeles. 1,000 times over. Why? What force pushes the moon away from Earth year after year, century after century, eon after eon? The answer is the same force that locked it in place, tidal friction. Except this time, it's not the moon's tides that matter. It's ours. Let's rewind for a moment and look at what's happening to Earth while all this lunar locking was taking place. Earth has tides, massive tides. Twice a day, the ocean rises and falls, pulled by the moon's gravity into those two bulges. We talked about earlier, one facing the moon, one on the opposite side. But here's the critical detail. Earth rotates faster than the moon orbits. Right now, Earth spins once every 24 hours, but the moon takes 27.3 days to orbit once. That means Earth is constantly rotating underneath those tidal bulges, trying to drag them along. The bulges want to stay aligned with the moon. Earth's rotation tries to drag them ahead. The result? Friction. Specifically friction between the ocean water and the seafloor, between the moving tides and the stationary continents. That friction slows Earth's rotation, gradually, incrementally, but measurably. Right now, Earth's day is getting longer by about 1.7 milliseconds per century. That's a tiny amount you'd never notice it in a lifetime. But over geological time, it adds up dramatically. Scientists can actually measure this. Not by watching clocks slow down, that would require precision beyond our instruments, but by looking backward in time through geological records. Ancient coral fossils, for instance, show daily growth rings similar to tree rings. By counting the rings between annual markers, paleontologists can determine how many days were in a year when that coral was alive. Coral from 400 million years ago shows approximately 400 days per year. That means each day was only about 22 hours long. Earth was spinning faster, the moon was closer, and the tides were stronger, more frequent, more dramatic. Go back even further, back to when the moon first formed 4.5 billion years ago, and Earth's day was only about 6 hours long. The planet was spinning so fast that the equator bulged outward, that hurricanes would have been impossible to form, that the Coriolis effect was dramatically different from today. And it's all been slowing down. All 4.5 billion years of Earth's history has been a story of gradually longer days, gradually weaker tides, gradually more stable rotation. The moon did this to us. The moon is still doing it to us. But where does that rotational energy go? Energy can't just disappear. The first law of thermodynamics demands conservation. Some of it converts to heat through friction, warming the oceans ever so slightly as they slosh back and forth against the seafloor. But most of it transfers to the moon as orbital energy. Here's how the tidal bulges on Earth don't align perfectly with the moon. Because Earth rotates faster than the moon, orbits the bulges get dragged slightly ahead of the moon's position. The near side bulge ends up a little bit ahead of the line connecting Earth and moon. Now that misaligned bulge has mass. And mass has gravity, so the bulge pulls on the moon, gravitationally tugging it slightly forward in its orbit. That forward tug adds energy to the moon's orbit. And in orbital mechanics, adding energy means moving to a higher orbit. The moon spirals outward, gaining altitude, trading orbital speed for distance. The numbers are precise and elegant. The rotational energy Earth loses exactly equals the orbital energy the moon gains minus the small amount dissipated as heat. The books balance. The universe keeps its accounts straight. And the result is a moon that's slowly, steadily, inexorably drifting away from us at 3.8 centimeters per year. We can actually measure this drift directly using technology left behind by the Apollo astronauts. Between 1969 and 1972, Apollo missions 11, 14, and 15 placed retroreflector arrays on the moon's surface, clusters of special mirrors designed to reflect light directly back toward its source. Scientists on Earth fire laser pulses at these reflectors. The light travels to the moon, bounces off the mirrors, and returns to Earth. By measuring the round-trip travel time, about 2.5 seconds, we can calculate the distance to the moon with millimeter precision. And when you do this repeatedly over years and decades, you see the pattern. Clearly, the moon is receding at 3.8 centimeters per year. Some years it's 3.7, some years it's 3.9, but the average is consistent, reliable, measurable. This is one of the most direct confirmations we have of tidal theory. The math predicts the moon should recede at roughly this rate based on Earth's rotation ocean tides and the mechanics of angular momentum transfer. And reality matches the prediction almost perfectly. The moon is leaving us. We can prove it. We can measure it. We can watch it happening in real time. Now, 3.8 centimeters per year doesn't sound like much. And over a human lifetime, say 80 years, the moon only recedes by about 3 meters. Barely noticeable. The moon would appear fractionally smaller in the sky, but not enough for your eyes to detect. But over deep time, the distances become staggering. 4.5 billion years ago, the moon formed at roughly 22,000 kilometers from Earth. Today, it's at 384,000 kilometers. That's an increase of 362,000 kilometers, more than 17 times its starting distance. At the current recession rate of 3.8 centimeters per year, you'd need about 9 billion years to cover that distance. But the moon has only existed for 4.5 billion years. How does that math work? The answer is that the recession rate wasn't constant. It was much faster in the early solar system, when the moon was closer and tidal forces were stronger. As the moon moved farther away, the tidal forces weakened and the recession slowed. Scientists estimate that the early moon may have been receding at rates of several meters per year, more than 100 times faster than today. The recession follows an inverse relationship with distance double the distance, and the recession rate drops by roughly a factor of 8, because tidal force falls off with the cube of distance, and recession rate depends on tidal force. So, the moon's journey away from Earth has been decelerating over time. It fled rapidly at first, then slowed to a steady retreat, and will continue slowing as the distance grows. Let's think about what this means for eclipses. Solar eclipses happen when the moon passes between Earth and Sun, blocking sunlight. Right now, the moon is almost exactly the right size and distance to perfectly cover the sun's disk during a total solar eclipse. The sun is 400 times wider than the moon, but it's also 400 times farther away, so they appear the same size in our sky. This is a cosmic coincidence. There's no physical reason it has to be this way. It just happens to be true right now in this particular epoch of Earth's history. But it won't always be true. As the moon recedes, it will appear smaller in the sky. Eventually, in about 600 million years, the moon will be too far away to completely cover the sun. Total solar eclipses will become impossible. We'll only have partial and annular eclipses where a ring of sunlight remains visible around the moon's silhouette. Humanity evolved during a brief window of cosmic time when total solar eclipses are possible. Our ancestors saw them, we see them, but our distant descendants, if humanity survives that long, will not. The universe doesn't owe us eclipses. We just happen to exist during the moment when the geometry works out. Lucky timing, cosmic accident, a gift we didn't ask for and won't keep forever. There's another consequence of the moon's recession that's less obvious but perhaps more profound. Earth's rotation will continue slowing. Right now, Earth's day is 24 hours long and getting longer by 1.7 milliseconds per century. That's slow, but it's relentless. Over hundreds of millions of years, it adds up. In about 2 billion years, assuming the tidal friction continues at similar rates, Earth's day could be 30 hours long, then 40, then 50. Eventually, billions of years from now, Earth's day will lengthen to match the moon's orbital period. At that point, Earth will be tidally locked to the moon, just as the moon is currently locked to Earth. The same side of Earth will face the moon always. The moon will hang motionless in the sky for half the planet, while the other half never sees it at all. But here's the catch. This will take an extraordinarily long time. Current estimates suggest it would take about 50 billion years for Earth to become tidally locked to the moon at the current recession rate, 50 billion years. The sun will die in about 5 billion years. It will expand into a red giant, possibly engulfing both Earth and moon, definitely rendering them uninhabitable long before tidal locking completes. So, Earth will never actually lock to the moon. The sun will end the game before the game ends naturally. Still, the direction is clear. The trend is obvious. Earth and moon are moving toward mutual tidal locking, even if they'll never arrive. Let's compare this to another system that did complete the process, Pluto and Charon. Pluto's largest moon. Charon is about half Pluto's diameter, much larger relative to its planet than our moon is to Earth. The two are so close in size that they orbit around a common center of mass located in empty space between them, not inside either body. Some astronomers consider them a binary planet system rather than a planet and moon, and they're mutually tidally locked. Charon always shows the same face to Pluto. Pluto always shows the same face to Charon, both locked, both frozen in their gravitational embrace, both staring at each other across the darkness, never looking away forever. This happened because Pluto is small and Charon is relatively large, so tidal forces could work on both bodies simultaneously. Pluto's day slowed to match Charon's orbit, and Charon's rotation, which was already locked, stayed locked. They reached equilibrium together. From Pluto's surface, if you're on the Charon-facing hemisphere, Charon hangs motionless in the sky. It doesn't rise or set. It just stays there, rotating slowly through its own day-night cycle, but never moving from its position in the sky. A permanent companion. An eternal watchman. From the opposite hemisphere of Pluto, Charon never appears at all. There are places on Pluto where if you lived there, you'd never see Charon, never even know it existed, unless you walked around to the other side of the planet. That's the future Earth and Moon are drifting toward, even though they'll never arrive. But why does the Moon's recession matter to us beyond curiosity? Why should we care that the Moon is leaving? One reason is tides. As the Moon recedes, tidal forces weaken. The difference isn't huge over human timescales, but over millions of years it becomes noticeable. Weaker tides mean less mixing in coastal oceans, less nutrient cycling, less energy dissipated in tidal bores and coastal flooding. Some scientists suggest that strong tides in Earth's early history may have been crucial for the origin of life. Tidal pools regions repeatedly flooded by seawater and then exposed to air and sunlight create conditions where organic molecules can concentrate, react, and potentially form the first self-replicating systems. If that's true, then the moon's proximity 4 billion years ago wasn't just a detail of Earth's early history. It may have been essential for our existence. Life on Earth might owe its origin in part to tides that no longer exist at the same intensity. The moon is leaving, and in some sense it's leaving behind the conditions that made us possible. There's also the question of Earth's axial stability. Right now, Earth's axis is tilted at 23.5 degrees relative to its orbital plane. That tilt gives us seasons summer and winter, the rhythms of climate that shape ecosystems and agricultural cycles. But Earth's axis isn't perfectly stable. It wobbles slightly, a motion called precession, completing a full cycle every 26,000 years. The moon's gravitational influence helps stabilize that wobble, preventing it from becoming chaotic. Without the moon, computer models suggest Earth's axial tilt could vary wildly over millions of years, swinging from near 0 degrees. No seasons, permanent ice caps, equatorial deserts to extreme values of 60 degrees, or more catastrophic seasonal variations, climate chaos. Mars, which has 2 tiny moons with negligible stabilizing influence, shows exactly this kind of axial chaos. Its tilt has varied from 0 to 60 degrees over its history, creating dramatic climate swings that may have contributed to the loss of its atmosphere and the disappearance of surface water. Earth's climate stability, the relatively predictable seasons that allowed complex life to evolve and civilizations to develop agriculture may depend critically on the moon's stabilizing presence. And as the moon recedes, that stabilizing influence weakens, though far too slowly to matter on human timescales. Still, it's a reminder the moon isn't just a light in the night sky. It's a gravitational anchor, a climate regulator, a cosmic partner that's shaped Earth's evolution in ways we're only beginning to understand. So, when you look up tonight and see that familiar face, remember it's farther away than when you were born, farther than when your grandparents were born, farther than when the pyramids were built or the first humans painted on cave walls. The moon is patient, but it's moving, retreating. Carrying with it the rotational energy Earth is slowly losing, converting our spin into distance, turning our shared history into separation. It's not dramatic, it's not sudden, but it's real. And it's been real for as long as the moon has existed. The moon is leaving us. Not today, not tomorrow, not in any time frame we'll live to see. But it's leaving nonetheless, following the mathematics of orbital mechanics, obeying the laws that govern all things in motion. And yet, despite this slow farewell, the moon's face never changes. It still shows us the same side it locked into place 3 billion years ago, still holds that gaze across the growing distance. But that face isn't quite as fixed as we've assumed. There's a subtle motion, a gentle wobble that allows us to peek just beyond the edges to catch glimpses of what lies just around the curve. The moon is locked. We've established that. One face toward Earth always. The same craters, the same Maria. The same patterns our ancestors memorized and named thousands of years ago. But if you watch carefully, if you photograph the moon night after night, month after month, and compare the images, you'll notice something strange. The moon wobbles. Not much, not dramatically, but enough that features near the edge, near the limb, sometimes slip into view and sometimes disappear beyond the curve. Enough that we can actually see 59% of the moon's surface from Earth, not just the 50% that strict tidal locking would allow. The moon is locked, yes, but it's not perfectly still. It dances. A slow, gentle waltz that reveals secrets at the edges that lets us peek just beyond what we're supposed to see. This motion has a name libration, and it's one of the most elegant demonstrations of orbital mechanics you'll ever encounter. Let's start with a common misconception. Many people assume that tidally locked means perfectly frozen, perfectly aligned, never moving even slightly, like a ball attached to a rigid rod, rotating in perfect synchronization, with no deviation whatsoever. But reality is messier than that. Orbits aren't perfect circles. Rotation axes aren't perfectly aligned. The universe doesn't do perfectly very well. It does close enough and then lets the wobbles and variations happen within that framework. Libration is what happens when tidal locking meets the real imperfect geometry of celestial mechanics. The moon is locked, but it's locked loosely. It can wiggle within certain constraints, like a door that's closed but not latched mostly in place, but still able to move slightly. And those slight movements add up to something we can see, measure, and use to explore more of the lunar surface than simple locking would allow. There are three main types of libration, each caused by different geometric effects. Let's explore them one by one, starting with the most significant libration in longitude. The moon's orbit around Earth isn't a perfect circle. It's an ellipse slightly elongated with Earth at one focus of that ellipse. This means the moon's distance from Earth varies throughout its orbit. At closest approach, called perigee, the moon is about 363,000 kilometers away. At farthest point, called apogee, it's about 405,000 kilometers away. That's a difference of 42,000 kilometers, more than 10% variation in distance. And that variation has consequences. When the moon is closer to Earth, it moves faster in its orbit. When it's farther away, it moves slower. This is Kepler's second law of planetary motion. A line drawn from Earth to the moon sweeps out equal areas in equal times, which means the moon must move faster when closer and slower when farther to keep the areas equal. But here's the key. While the moon's orbital speed varies, its rotation speed stays nearly constant. The moon spins on its axis at the same rate, regardless of whether it's at perigee or apogee. So, at perigee, the moon is moving faster in its orbit than it's rotating. Its orbital motion outpaces its spin. The result? We see slightly past the western edge of the near side, about 7.9 degrees extra longitude. At apogee, the opposite happens. The moon is moving slower in its orbit than it's rotating. Its spin outpaces its orbital motion. We see slightly past the eastern edge again, about 7.9 degrees. Over the course of one orbit, 1 month, the moon appears to rock back and forth, revealing first one edge, then the other. East, then west. West, then east. A slow oscillation like a pendulum swinging in the sky. This wasn't obvious to ancient astronomers. The motion is too slow, too subtle to notice casually. But once telescopes were invented and people started mapping the moon's features precisely, they noticed that crater positions near the limb changed slightly from night to night. The Italian astronomer Giovanni Riccioli, working in the 1650s, was one of the first to document this systematically. He noticed that Mare Orientale, the eastern sea, which he named for its position near the eastern limb, sometimes appeared fully visible and sometimes slipped partially beyond the edge. He correctly attributed this to a wobbling motion, though he didn't fully understand the mechanism. Isaac Newton later explained libration mathematically in his Principia, showing that it was a natural consequence of the moon's elliptical orbit combined with its constant rotation rate. The moon wasn't actually wobbling. We were seeing it from different angles. As the geometric relationship between Earth-Moon and the orbital path shifted throughout the month. It's a perspective effect, like watching a spinning carousel from different positions. The carousel isn't changing speed, but depending on where you stand and how fast you're walking, it appears to move faster or slower relative to your view. The second type of libration is libration in latitude. This one is caused by the tilt of the moon's rotation axis. The moon's axis isn't perpendicular to its orbital plane. It's tilted by about 6.7 degrees. This might not sound like much, but it's enough to create a noticeable effect. Imagine looking at a globe tilted on its axis. From one viewing angle, you can see more of the North Pole. From another angle, you can see more of the South Pole. The globe isn't moving, but your perspective reveals different amounts of each hemisphere depending on your position. The moon works the same way. As it orbits Earth, our viewing angle relative to its rotation axis changes. Sometimes we're looking slightly down at the North Pole, seeing a bit more of the northern lunar hemisphere. Half an orbit later, we're looking slightly up at the South Pole, seeing a bit more of the southern hemisphere. This libration in latitude lets us see about 6.9 degrees extra above and below the equator at different times of the month. Not as much as the longitude libration, but still significant. Combined with longitude libration, this means we can see features near both the edges and the poles that would otherwise be hidden. Mare Humboldtianum near the North Pole, Mare Australe near the South Pole, both are visible thanks to latitude libration, even though they're technically on the cusp between near and far sides. The third type of libration is called diurnal libration, and this one is caused by Earth's rotation, not the moon's motion. Here's how it works. When the moon rises in the east, you're standing on the eastern edge of Earth relative to the moon. When it sets in the west, you're on the western edge. That's a shift in viewing position of about 12,700 kilometers Earth's diameter. 12,700 kilometers isn't much compared to the Earth-Moon distance of 384,000 kilometers. It's only about 3%, but it's enough to shift your perspective by roughly 1 degree, allowing you to see slightly around the western edge when the moon rises and slightly around the eastern edge when it sets. This effect is small compared to the other librations, only about 1 degree total, but it adds to the overall wobble. And for observers near Earth's equator, where the effect is strongest, it can make a meaningful difference in what features are visible at moonrise versus moonset. Diurnal libration is also the only type of libration that changes over the course of a single night. Longitude and latitude libration are monthly cycles, but diurnal libration happens within hours as Earth rotates and your position changes. If you're dedicated enough to photograph the moon at moonrise, then again at midnight, then again at moonset, you'll see the eastern and western limbs shift slightly between those observations. The moon isn't moving. You are. And that movement changes what you can see. So, when you add up all three types of libration, longitude, latitude, and diurnal, the total effect is substantial. Instead of seeing exactly 50% of the moon's surface, we can see about 59% over time. That extra 9% is significant. It's an area roughly equivalent to the size of Libya or Mongolia. It's not nothing. It's a substantial fraction of the moon that would be hidden without libration, but becomes visible thanks to these geometric wobbles. And here's the beautiful part, that 59% includes some genuinely fascinating terrain. Mare Orientale, for instance, the eastern sea we mentioned earlier, is one of the youngest and best preserved impact basins on the moon. It's surrounded by concentric rings of mountains, like ripples frozen in stone, marking where the impact shock wave compressed and fractured the crust. Mare Orientale is right on the edge. It's only visible during favorable libration, when the moon rocks westward enough to bring it into view. Without libration, we'd never see it from Earth. We'd know about it only from spacecraft photographs, but thanks to the moon's wobble, amateur astronomers with backyard telescopes can glimpse it during certain phases of certain months. That's the gift of libration. It expands our view without requiring us to leave Earth's surface. There's a fourth type of libration worth mentioning, though it's much smaller than the others: physical libration. This is an actual wobble in the moon's rotation, not just a viewing angle effect. Remember, the moon isn't a perfect sphere with uniform density. It has mass concentrations mascons beneath some of the Maria, and its shape is slightly elongated toward Earth. These irregularities mean the moon's moment of inertia isn't constant in all directions. When combined with tidal forces from Earth, these irregularities cause the moon to rock very slightly on its axis. It's like a spinning top that wobbles as it slows down, except the moon's wobble is tiny, only a few arc minutes far smaller than the other librations, and it happens over complex cycles involving multiple orbital periods. Physical libration was predicted mathematically before it was observed, another triumph of Newtonian mechanics. It's a reminder that even tidally locked doesn't mean perfectly frozen. The universe allows wobble. It allows deviation. It allows imperfection within stability. Here's a question worth pondering. If libration allows us to see 59% of the moon's surface, what about the other 41%? That truly hidden region that no amount of libration ever reveals, that 41% remained completely unknown until the space age. No telescope could see it. No libration could reveal it. It was genuinely invisible from Earth, a blank spot on our maps, until spacecraft could fly around the moon and photograph it directly. When Luna 3 photographed the far side in 1959, some of what it captured was actually the libration zones, the 59% we can already see from Earth, just photographed from a different angle. But the rest was virgin territory never seen before by any human or instrument. And what did they find? We talked about this earlier. More craters, fewer Maria, thicker crust. But what's striking is how sharp the boundary is between the familiar 59% and the truly hidden 41%. There's a region called the limb, where features sometimes peek into view during favorable libration and sometimes disappear. Craters right on that boundary have been watched and studied from Earth for centuries, their visibility coming and going with the monthly cycle. But just beyond that boundary, just past the limb, lies territory that remained completely unknown until we could send cameras there. A boundary marked not by geology or composition, but purely by geometry, by the accident of where the libration limits happen to fall, given the moon's orbital parameters. Some people ask if we can see 59% of the moon. Why not 60 or 65? What determines the exact limit? The answer comes down to the magnitude of the orbital eccentricity, the axial tilt, and Earth's radius. These numbers aren't arbitrary. They're determined by the moon's formation, history, tidal evolution, and orbital dynamics. But they're also not special. If the moon's orbit were slightly more elliptical, we'd see a bit more. If it were more circular, we'd see a bit less. 59% is what we get, given the specific parameters of the Earth-Moon system. It's not designed for us. It's not optimized for visibility. It just is what it is, the result of billions of years of gravitational interaction settling into the current configuration. And yet, there's something almost generous about it. The universe didn't have to give us libration. A perfectly circular orbit with zero axial tilt would still be tidally locked, still show us one face, but only exactly 50%. We'd be locked out of 9% of the near side, never seeing those edge regions, never glimpsing Mare Orientale or the polar features. Instead, we get wobble. We get perspective shifts. We get just enough variation to expand our view without breaking the lock. It's like a friend who keeps a secret but occasionally drops hints at the edges. You can't know the full story, but you know more than you're supposed to. You can piece together clues from the fragments that slip into view. For lunar cartographers, scientists who map the moon's surface, libration is both a blessing and a challenge. It's a blessing because it gives more surface to study from Earth. It's a challenge because features near the limb appear distorted, foreshortened, viewed at an extreme angle that makes accurate mapping difficult. Imagine trying to draw a circle while looking at it edge-on. It appears as an ellipse squashed flat, its true shape obscured by perspective. That's what happens to lunar features near the limb. Craters that are actually circular appear oval-shaped. Mountains that are actually tall appear compressed. Distances become hard to judge. Early lunar mappers struggled with this. They knew libration let them see more, but they also knew the geometry was complicated. Features had to be corrected for foreshortening angles, had to be recalculated. Multiple observations from different libration phases had to be combined to build an accurate picture. Modern digital mapping uses spacecraft data, which eliminates the libration problem entirely. You just photograph from directly overhead. But for centuries, understanding libration was essential to understanding the moon's true geography. And even now, amateur astronomers who want to observe near-limb features need to know the libration schedule. When is Mare Orientale most visible? When does the North Pole tip into view? There are charts, predictions, software that calculates optimal viewing times based on libration phases. The wobble matters, the dance matters, and knowing the steps lets you see more than casual observation ever could. So, the next time you look at the moon, remember that face isn't quite as fixed as it seems. It's dancing, slowly, subtly, a waltz choreographed by orbital mechanics performed over the course of weeks and months, revealing hints at the edges of mysteries just beyond sight. The moon is locked. But within that lock, there's freedom. There's movement. There's space for the imperfect, the asymmetric, the wonderfully complex geometry that makes the real universe so much richer than idealized models. Tidal locking doesn't mean frozen stillness. It means synchronized motion. And within that synchronization, there's room for variation, for libration, for the gentle wobble that lets us see just a little more than we're supposed to. But Earth and Moon aren't the only dancers in the solar system. Other worlds perform similar waltzes, other moons show faces locked and librating. And by looking at them, we can understand our own moon story in a broader context. Out beyond Mars in the realm of the gas giants, there's a moon called Io, Jupiter's innermost large satellite, a world painted in yellows and oranges and reds, its surface constantly reshaping itself through volcanic eruptions that never stop. Io is tidally locked to Jupiter, just like our moon is locked to Earth, always showing the same face to its planet, always held in that gravitational grip. But Io's story is different, violent where ours is gentle, active where ours is quiet. A reminder that tidal locking isn't just one story. It's a pattern repeated across the solar system each time, with different consequences, different timelines, different worlds shaped by the same fundamental forces. Our moon's locked face is a curiosity, an astronomical fact that makes us wonder. But across the solar system, tidal locking tells dozens of stories, each one revealing something about how gravity sculpts worlds over deep time. Let's take inventory of what we know. How common is tidal locking? Is our moon special, or is this the default state for satellites everywhere? The answer is striking. Tidal locking is incredibly common. It's almost the rule rather than the exception for moons in the solar system. All 4 of Jupiter's large moons, the Galilean satellites discovered by Galileo in 1610, are tidally locked. Io, Europa, Ganymede, and Callisto each show one face permanently toward Jupiter. Saturn's largest moon Titan is locked. So is Triton, Neptune's major moon. Even tiny moons orbiting close to their planets tend to lock relatively quickly. In fact, scientists estimate that most moons in the solar system that have been in their current orbits for more than a few 100 million years are tidally locked. It's the natural endpoint of tidal evolution. Given enough time and close enough proximity, the mathematics demands it. So, our moon isn't unique. It's following a script written by gravity, a script that plays out wherever moons orbit planets. But here's where it gets interesting. The timeline for tidal locking varies dramatically depending on the moon's distance from its planet and the planet's mass. Io locked fast, incredibly fast, by geological standards. Scientists estimate Io became tidally locked within just a few million years of its formation, maybe even less. Why? Because Io orbits only 422,000 kilometers from Jupiter's center, and Jupiter is 318 times more massive than Earth. The tidal forces on Io are immense. Jupiter's gravity doesn't just lock Io's rotation, it actively heats the moon's interior through constant tidal flexing. We mentioned this earlier, but it's worth emphasizing Io has over 400 active volcanoes. Its surface is being resurfaced at a rate of about 1 centimeter per year, which means the entire surface you see today didn't exist a few million years ago. That's tidal heating in overdrive. Io's orbital energy is constantly being converted into heat through friction as Jupiter's gravity squeezes and releases the moon with each orbit. The moon is literally being cooked from the inside by tidal forces. and those same forces locked Io's rotation almost immediately after it formed. There was never a period where Io spun freely, showing Jupiter all its sides. The lock happened fast, and it's held ever since. Compare that to Callisto, Jupiter's outermost Galilean moon. Callisto orbits at 1,883,000 kilometers, more than 4 times farther from Jupiter than Io. The tidal forces are much weaker out there, inversely proportional to the cube of distance. Callisto still locked, but it took much longer, perhaps hundreds of millions of years. And once locked, Callisto doesn't experience the violent tidal heating that Io does. Its interior is cold, quiet, ancient. Its surface is the most heavily cratered in the solar system, suggesting it hasn't been geologically active for billions of years. Same planet, same fundamental physics. But distance makes all the difference. Close orbit means fast locking and ongoing tidal heating. Distant orbit means slow locking and minimal ongoing effects. The pattern holds across all the moons we've studied. Distance determines timeline. Mass determines intensity. But the endpoint is almost always the same tidal lock. Europa, Jupiter's second Galilean moon, tells perhaps the most intriguing story. Europa is tidally locked to Jupiter, showing the same face always. But Europa is also caught in what's called orbital resonance with Io and Ganymede. Here's how it works. For everyone, orbit Europa completes Io completes exactly 2 orbits, and Ganymede completes exactly half an orbit. The 3 moons are synchronized not in their rotation, but in their orbital periods. This resonance is stable and self-reinforcing through gravitational interactions. But here's the consequence. Europa's orbit isn't circular. The resonance with Io and Ganymede keeps Europa's orbit slightly elliptical, which means Europa's distance from Jupiter varies throughout each orbit, which means the tidal forces vary in strength. When Europa is closer to Jupiter, the tidal bulge is larger. When it's farther, the bulge is smaller. But Europa's rotation stays constant because it's locked. So the solid ice shell is constantly being squeezed and released, flexed and deformed, creating friction and heat. That tidal heating keeps Europa's subsurface ocean liquid. Beneath the frozen surface, beneath 15 to 25 kilometers of ice, there's an ocean of liquid water that may be 100 kilometers deep, possibly the largest ocean in the solar system, by volume larger than all of Earth's oceans combined. And it exists because of tidal locking, combined with orbital resonance. Europa is locked to Jupiter, but the resonance prevents the orbit from becoming perfectly circular, which keeps the tidal heating active, which keeps the ocean liquid. Life might exist in that ocean. Microorganisms clinging to hydrothermal vents on the ocean floor, deriving energy from chemical reactions rather than sunlight. We don't know yet, but future missions will find out. And if life does exist there, it will owe its existence in part to tidal locking, to the same gravitational dance that locked our moon into its eternal gaze at Earth. Let's shift to Saturn and look at Titan, the second largest moon in the solar system and the only moon with a substantial atmosphere. Titan is tidally locked to Saturn, one face toward the planet always. But Titan's thick atmosphere, denser than Earth's at the surface, complicates the story in fascinating ways. The atmosphere creates weather, methane clouds, methane rain rivers, and lakes of liquid methane and ethane on the surface. Wind patterns, seasonal variations, complex circulation systems. And this weather doesn't respect the tidal lock. Winds blow in directions determined by atmospheric dynamics, not by Saturn's position. So, while Titan's solid body is locked to Saturn, its atmosphere is not. The air moves freely, creating a disconnect between the surface rotation and the atmospheric circulation. It's like Earth. In that sense, our solid planet rotates at a different rate than our winds blow. But here's what's interesting. Scientists believe Titan's interior might have a subsurface ocean, similar to Europa. If that ocean exists, it would be sandwiched between the icy crust and a rocky core, decoupled from the surface by a layer of liquid. This creates a strange situation where Titan's icy shell is locked to Saturn, but the ocean beneath might rotate independently, and the atmosphere above definitely rotates independently. 3 layers, 3 different rotation regimes, all on one moon. Tidal locking in this case only applies to the visible surface. Beneath and above the story is more complex. Now, let's look at an exception. Hyperion, a small, irregularly shaped moon of Saturn that's not tidally locked, despite orbiting relatively close to the planet. Hyperion is chaos incarnate. It tumbles unpredictably its rotation period, varying wildly, its orientation essentially random. You can't predict which side will face Saturn at any given time, because Hyperion itself doesn't know which side should face Saturn. Why? Because Hyperion is irregularly shaped, roughly potato-shaped, and its orbit is perturbed by nearby Titan's gravity. The combination means there's no stable orientation for tidal forces to lock onto. Every orientation has similar energy, so Hyperion tumbles chaotically between them. This is rare. Most moons, given enough time, find some orientation that's lower energy than the others and lock into it. But Hyperion is caught in a special condition, chaotic rotation, where no orientation is stable. It's a reminder that tidal locking requires certain conditions: regular shape, stable orbit, enough time, strong enough tidal forces. Break any of those conditions, and the lock might never form. Hyperion has been tumbling chaotically for millions or billions of years. It might tumble forever, or it might eventually settle into a lock if its orbit stabilizes or its shape changes through impacts. But for now, it's the exception that proves the rule. Let's venture farther out to Neptune and look at Triton, one of the strangest moons in the solar system. Triton is tidally locked to Neptune, but Triton orbits backward retrograde opposite to Neptune's rotation. This is almost certainly because Triton didn't form alongside Neptune. It was captured, likely a Kuiper belt object that wandered too close and got gravitationally trapped. When Triton was first captured, its orbit was probably highly elliptical and chaotic, but tidal forces circularized that orbit over hundreds of millions of years, and those same forces locked Triton's rotation. The locking process would have generated enormous amounts of heat. Triton's interior probably melted, completely erasing any evidence of its original structure. The surface we see today formed after the capture, after the tidal heating, after the lock stabilized. And here's the grim future: Triton is still spiraling inward toward Neptune. Unlike our moon, which is spiraling outward, Triton is doomed. In about 3.5 billion years, Triton will cross Neptune's roach, limit the distance where tidal forces overcome the moon's own gravity, and Triton will be torn apart, forming a spectacular ring system around Neptune. Tidal locking didn't save Triton, it just delayed its destruction. But for now, Triton orbits faithfully, showing Neptune the same face a captured prisoner held in gravitational chains. Beyond our solar system, tidal locking becomes even more dramatic. Exoplanets, planets orbiting other stars, often orbit very close to their suns, especially the ones we've discovered, because close-in planets are easier to detect. Many of these exoplanets are thought to be tidally locked to their stars. One hemisphere permanently faces the star, baked in eternal daylight. The other hemisphere faces away, frozen in eternal night. A world divided into fire and ice, with perhaps a narrow twilight zone in between, where temperatures might be habitable. Proxima Centauri, b, the nearest known exoplanet to Earth, is likely tidally locked. It orbits just 7.5 million kilometers from its star, much closer than Mercury is to our Sun. At that distance, tidal forces from the star would lock the planet's rotation within a few million years. If Proxima Centauri b has an atmosphere, winds might redistribute heat from the day side to the night side, making the twilight zone potentially habitable. But if it lacks an atmosphere, the day side might be too hot for liquid water, and the night side too cold, leaving the planet sterile despite being in the habitable zone. Tidal locking changes everything for these worlds: their climate, their potential for life, their very nature as planets, all shaped by the lock. And then there's the most extreme example of tidal locking in our solar system, Pluto and Charon. We mentioned this earlier, but it's worth revisiting because it's so unusual. Pluto and Charon are mutually tidally locked. Pluto always shows the same face to Charon, and Charon always shows the same face to Pluto. They orbit around a point in space between them, called the Barycenter Center. Both are frozen in their mutual gaze, neither ever seeing the other's far side from their respective surfaces. This happened because Pluto is small and Charon is relatively large. Charon is about half Pluto's diameter and 1/8 its mass. The tidal forces could work on both bodies simultaneously. Pluto slowed Charon's rotation until Charon locked. Then Charon slowed Pluto's rotation until Pluto locked too. Now they orbit each other, synchronized eternal. From Pluto's Charon-facing hemisphere, Charon hangs motionless in the sky, never rising, never setting, just rotating slowly through its phases. From Pluto's opposite hemisphere, Charon never appears at all. It's the endpoint of tidal evolution. Not just one body locked to another, but both locked to each other. A cosmic dance perfected. A gravitational marriage with no possibility of separation. So, what's the lesson here? What does this survey of tidally locked moons across the solar system teach us first? That tidal locking is universal. It's not unique to Earth and Moon. It's a fundamental process that happens wherever moons orbit planets and wherever planets orbit close to stars. The mathematics of gravity doesn't care which system it's operating in. The same equations apply everywhere. Second, that distance and time determine everything. Close moons lock fast, distant moons lock slow. But given enough time, almost everything locks eventually. Third, the tidal locking has consequences beyond rotation. It generates heat, maintains oceans, tears moons apart, shapes climates on exoplanets. It's not just an interesting geometric fact, it's a force that actively sculpts worlds. And fourth, that our moon story is typical, not special, not unique. Just one example among dozens of moons following the same script, locked by the same forces shaped by the same patient mathematics of orbital mechanics. When we look at our moon and see that familiar face held eternally toward Earth, we're not seeing something rare, we're seeing something universal. A pattern repeated across the cosmos, a dance performed by moons everywhere, a lock that gravity imposes on all satellites given enough time and proximity. Our moon shows us one face. So does Io, so does Europa, so does Titan, Triton, Charon. The names change, the planets change, but the pattern remains. Tidal locking is the rule, not the exception. And understanding that seeing our moon as part of a larger family of locked worlds helps us appreciate just how ordinary, and yet how profound the forces are that shape the companion we see in our night sky. But there's one final layer to this story. One last thing we need to understand about the moon's eternal gaze. Because that face, that familiar pattern of light and shadow, isn't quite as eternal as we've been assuming. Tonight, when you step outside and look up, you'll see a face you've known your entire life. The same patterns, the same shadows, the same quiet companion that's been watching over humanity since before we had words for moon or wonder or home. But now you know the secret behind that constancy. You know that face isn't frozen by choice. It's held there by forces that began 4.5 billion years ago, when a world called Theia collided with Earth and threw debris into orbit. Forces that grabbed the newborn moon when it was close enough to touch and never let go. You know that what looks like stillness is actually motion. A rotation so perfectly synchronized with the moon's orbit that the same side always faces us like a dancer, spinning in place while circling a partner. You know that tidal friction spent 1 billion years slowing the moon's spin, converting the chaos of rapid rotation into the peace of locked synchronization, one imperceptible degree at a time. The moon shows us one face because gravity is patient, because time is long, because the universe follows mathematics that doesn't care about human scales of perception, but plays out regardless, shaping worlds across eons. 4.5 billion years ago, both Earth and Moon were spinning fast days measured in hours, both worlds showing all their faces to each other in rapid succession. The Moon was so close, it filled half the sky, a glowing disk that would have been terrifying if anyone had been there to see it. But no one was there. Just molten rock and impact craters and volcanic plains still cooling from the violence of formation. Slowly, over hundreds of millions of years, Earth's gravity reached into the Moon and found the asymmetries, the denser regions, the slight elongation pointing toward us. The mass concentrations that made one orientation slightly more favorable than the others. And gravity pulled, not hard, not suddenly, but constantly. Every rotation created friction as the tidal bulge tried to stay aligned with Earth. Every orbit dissipated a tiny amount of energy as heat. Every million years, the Moon's spin slowed by fractions of a degree. Until one day, though, no consciousness marked it. Though the universe didn't notice, the Moon's rotation period matched its orbital period exactly. 27.3 days to spin once. 27.3 days to circle Earth once. Locked. And it's been locked ever since. For 3 billion years, the Moon has held this pose. Through the formation of Earth's continents, through the rise of oxygen in our atmosphere, through the evolution of single cells into complex life, through the age of dinosaurs and their extinction, through the emergence of mammals and eventually humans. Every ancestor who ever looked up at the night sky saw the same lunar face you see tonight. The same Maria forming the man in the moon or the rabbit pounding rice. The same bright highlands, the same scattered craters. Australopithecus saw it 3 million years ago. Homo erectus saw it 1 million years ago. Every human culture that ever existed saw it and named it and wove stories around those unchanging patterns. The Moon has been our constant companion, not by choice, not by design, but by the mathematics of orbital mechanics playing out over deep time. But here's what makes it even more poignant. The Moon is leaving us. 3.8 centimeters per year. The width of 2 fingers. The rate your fingernails grow. The same tidal forces that locked the Moon in place are now pushing it away. Earth's rotation is slowing our days growing longer by milliseconds per century. And that lost rotational energy is transferring to the Moon's orbit, pushing it higher, farther into the darkness. 4.5 billion years ago, the Moon was 22,000 kilometers away. Today, it's 384,000 kilometers away. It's traveled farther than the distance across the United States 1,000 times over. And it's still going. In 600 million years, the Moon will be far enough that total solar eclipses become impossible. That perfect alignment where the Moon's apparent size exactly matches the Sun's, creating those moments of totality where day becomes night and the corona blazes, that cosmic coincidence will end. Our descendants, if they exist, if they're still on Earth, will never see what we've seen. They'll never stand in the Moon's shadow and watch the Sun's atmosphere glow around the edges of that dark disk. We live in a brief window of cosmic time when total eclipses are possible, and we're lucky enough to be here for it. Eventually, billions of years from now, long after the Sun has started dying, Earth's rotation will slow enough that we too become tidally locked to the Moon. One side of Earth will face the Moon always. The other side will never see it. From the Moon-facing hemisphere, the Moon will hang motionless in the sky, never rising, never setting, rotating slowly through its phases, but staying fixed in position. A permanent companion, an eternal watchman. From the opposite hemisphere, the Moon will never appear. There will be places on Earth where, if you lived there, you'd never see the Moon at all, never know it existed, unless you traveled to the other side of the planet. But this will take 50 billion years, and the Sun will die in 5 billion years long before Earth can lock to the Moon. So, we'll never get there. The Sun will end the dance before the dance ends naturally. Still, the direction is clear. Earth and Moon are moving toward mutual tidal locking, following the same path that Pluto and Charon completed long ago. We're just not fast enough to finish before the universe moves on. There's something beautiful about that incompleteness, isn't there? The story of Earth and Moon will never have a final chapter. The sun will interrupt. The solar system will dissolve. But the slow, patient process of tidal locking will continue right up until the end. The moon will be drifting away when the sun expands into a red giant, still receding, still stealing Earth's rotational energy, still following the script written by gravity billions of years ago. And maybe that's fitting. Maybe perfect stories don't need endings. Maybe the best stories are the ones that continue beyond the final page implied, but never fully told. So, when you look up tonight and see that familiar face, those dark Maria, those bright highlands, that pattern you've known since childhood, remember what you're seeing. You're seeing the result of the longest gravitational embrace in the solar system. You're seeing a world that surrendered its free spin billions of years ago and found something more stable in return. You're seeing a companion that's been locked in its gaze at Earth, longer than complex life has existed. Longer than oxygen has been abundant in our atmosphere, longer than continents have held their current shapes. The moon doesn't choose to show us one face. Physics chose for it. Time chose for it. The mathematics of celestial mechanics wrote the script before the first human ever wondered why. But knowing the mechanism, understanding the forces, seeing the billion-year timeline, somehow makes it more beautiful, not less. Because the moon's loyalty isn't sentimentality, it's thermodynamics. It's the universe finding the lowest energy state and settling there. It's chaos transforming into order through the patient work of gravity across geological time. And there's a lesson in that, maybe, about patience, about how small forces applied consistently over vast time can reshape worlds, about how the universe doesn't hurry, but also doesn't forget. The moon didn't lock overnight. It took 1 billion years, but it locked completely permanently, irreversibly. The work was done slowly, but it was done thoroughly. That's how gravity operates. That's how tidal forces work. Not with sudden drama, but with persistent, inexorable pressure that eventually moves mountains, slows worlds, locks entire moons into eternal synchronization. Small forces, long time, total transformation. If there's anything we can take from the moon's story, it's that. Have you ever wondered what it would be like to stand on the far side, that hidden hemisphere that no human has ever walked on, that no Earth-based observer has ever seen directly? It's not dark, we know that now. It gets the same sunlight as the near side, but it is profoundly alone. Earth never rises there, never sets, never appears at all. Just stars and sun and the deep silence of a place where Earth's presence has never reached. Standing there, you'd be more isolated from Earth than anyone has ever been. Not because of distance, the Apollo astronauts went to the near side, which is the same distance, but because of visibility. You couldn't look up and see home. You couldn't radio directly to Earth. You'd need a relay satellite. The far side is truly far, cut off not by space, but by geometry. Hidden not by darkness, but by the accident of how the moon's mass distributed itself during tidal locking. Someday humans will walk there. Someday we'll build bases on the far side, set up radio telescopes shielded from Earth's electromagnetic noise study. The universe from a vantage point our world has never accessed. And when we do, we'll be visiting a place that has been waiting in silence for 4.5 billion years. A place where Earth is a myth. A place defined by absence. But tonight from here, Earth is everywhere the moon looks. The moon has been staring at us for 3 billion years, watching our atmosphere change color as oxygen appeared, watching continents drift, watching ice ages come and go, watching lights appear on the night side as civilization emerged. The moon has seen all of it, not consciously, not with intention. But it's been the witness to Earth's entire history since the tidal lock engaged. And it will keep watching. Keep holding that same pose. Keep showing us that same familiar face. until the sun dies, until the solar system dissolves, until gravity itself loses its grip as the universe expands into cold, dark eternity. But that's billions of years away. For now, tonight, the moon is there, constant, faithful, locked in the embrace that has defined both our worlds for longer than either of us can comprehend. So, step outside, look up, find that face you know by heart. And remember, you're not just seeing a moon, you're seeing the endpoint of billions of years of gravitational choreography. You're seeing proof that patience shapes worlds. You're seeing a companion that has never looked away, not because it loves us, but because physics demanded it. The moon shows us one side, not by choice, but by inevitability. And somehow, that makes it mean even more. Because in a universe of chaos and change, in a cosmos where nothing lasts forever and everything eventually decays, the moon's constancy, however it was achieved, feels like a gift. A face that never turns away. A companion that never leaves even as it slowly drifts farther into the night. A reminder that some things once established endure. The moon is locked, we are held, and together we drift through space bound by forces we didn't choose but can't escape. Thank you for drifting with me through this quiet exploration of tides and time, of gravity and deep history. Thank you for letting curiosity guide you through the mathematics of locked worlds and the poetry of patient forces. The moon will still be there when you wake. The same face, the same patterns, the same silent companion it's always been. And now you know why. Sleep well. Dream gently. And when you see the moon again, see it differently. Not just as a light in the darkness, but as a world held in an eternal embrace, showing us the face it's shown for 3 billion years and will show for billions more. Until we meet again, under the same sky, beneath the same moon, wondering about the next quiet mystery the universe has waiting for us. Good night.